Okay, so we're going to start with vectors, and we're going to start identifying things that are vectors and what vectors have to have. So vectors must have a magnitude, also known as a length, and a direction. Vectors must have a magnitude and a direction. Okay, they are geometric constructs. So we're going to be adding vectors and subtracting vectors and multiplying vectors, and there's a distinct geometry component to vectors. So in general, yes, we can add and subtract, but when we start doing things in different directions, then we have to start paying attention to angles, and we have to start paying attention to the triangles, and that's where vectors get a little bit more complicated. Okay, things that we already have that are vectors. Displacement. Uh-oh. That's not good. Displacement. Velocity. And acceleration are our primary vectors. These are the things we start with motion, and then other vectors come from these. So we've defined a new thing that comes from acceleration, right? That multiplies acceleration in there. Okay, like mass times acceleration is our what?
Force.
Is a force, right? So force, because force equals mass, which is a scalar, okay, and acceleration, okay, which is a vector. Okay, whenever we multiply by a vector, a scalar times a vector, we keep a vector. Okay, and a scalar just makes it bigger. And sometimes they do different terms. So our force is now also a vector because it has an acceleration component to it. Does that make sense? Okay. Forces also must have a magnitude. Okay, how much is the force? And a direction to it. Okay, and that generally comes from the acceleration. Okay, we're going to start with addition of vectors. Okay, and subtraction too. Okay, just like in regular math, if you add two vectors together, it doesn't matter which one you add first, which one comes first. Okay, but in subtraction, it does matter which one comes first. Okay, so we have, okay, and we're going to draw we're going to call that vector A. And we're going to call this vector B. Okay, when you add vectors together, you add them tip to tail. So, A plus B is going to equal the vector A okay, mind you, I'm trying to imitate this vector as much as I can. Same angle, right? Same general angle, same length. Okay, because the angle is the direction and the length, it represents the magnitude, although I could probably go a little bit longer for the length. A. Okay, B, we want to do the same thing, except we're going to put the tip of A at the tail of B. Okay, so I tried to duplicate this vector right here. Yeah? You guys following me with that? So the vector a plus b goes from the tail of the first one to the tip of the last. And that would be a plus b. You guys follow me there? That makes sense? Yeah, everyone? Okay. So that's addition. In fact, you could do it the other way. A plus b is the same thing as b plus a. So we could do b plus a, and then we would draw vector b, right? Okay, there's vector b. And then we add vector a to it. And we get and these two are pretty much the same vector, right? You guys see that? Okay. Subtraction is a little different. So if we do, now it's sort of a little different. Let's say we do a minus b. We could rewrite this as a plus negative b, right? According to our math rules, these two are equivalent statements, right? Okay. Well, whenever this negative here, this negative just means the opposite direction. So a negative b is actually this vector, except with the tip pointing the other direction. Yeah? All right, so if we're going to do that, then we get a tip to tail, but now if this vector b is the opposite direction, the tail is going to be here, and it's going to go that way rather than right. So that was positive b. This is negative b. And that's a. Yeah? Which leads us to it's a long way to draw. Is this making sense? Here we are. Okay. B minus A is different. But it should just be the opposite of this. It actually winds up being the opposite direction because those rules still apply. That let's say we did B minus A. Well, that would be the same thing as negative A minus B, right? Yes. Okay, I need some kind of acknowledgement if I'm looking up. So that B minus A, if I factor out a negative 1, that's going to give us negative 1 times negative B plus A, or A plus a negative B, which is the same thing as this up here, right? So instead of A minus B, B minus A would be right? Same vector, opposite direction. Okay, so that's addition and subtraction of vectors. Now, this is how they look graphically. So if I ask you guys to solve for vectors graphically, they kind of look like this. But the way we express them, and the way that you guys have been expressing them in your math classes so far, is based on a Cartesian coordinate system. And the best way that we do it is by putting the tail of our vector at the origin. Okay, and drawing our vectors from there. So, if that were the case, then A would look like, there we are. Okay, so here's our vector A again. Okay, and B I'm drawing it above the axis just so you guys can see it. And that's B. Okay. And these vectors are represented on here by their endpoints. This point right here is XA, Y for vector A. And this one here is X for vector B, Y for vector B. These parts, okay, so essentially it's the coordinate where the vector ends, right? So it's so much X this way, so much X this way and so much Y that way, and okay. So mathematically, if we're to add these, A plus B can now equal X of A plus X of B, Y of A plus Y of B. Right? So we can add the X's together, and we can add the Y's together, and that's going to give us our final value for A plus B. Okay, so what I'm going to do is I'm going to give you guys some sample values, and I want you to work these out. So this is going to be 5 and 3, and this is going to be -6 and 0. Okay, so if that's the case, and we add them together, what would our vector wind up being? Okay, so 5 plus a -6 is -1. 3 plus 0 is 3, right? So that becomes our third vector, -1, 3. So we're about there. And perhaps I'm exaggerating the -1. Okay, but that pretty much matches the vectors. Well, not really. Down here, actually, I made this shorter. Well, for these values that I gave you, that is the resultant of A plus B. Yeah? Okay, here's the beauty of this. These are called the components. The X value and the Y value are called the components. Okay, vectors have an X component and a Y component. They are orthogonal. We've used this term before, right? Okay, they are at right angles to each other. I could throw another dimension, and I could give you that dimension, right? Coming out of the page. And all of a sudden, that's a z-axis, right? And we can have vectors in 3 dimensions. And we would have an x component, a y component, and a z component. And all 3 of those are orthogonal to each other. Yeah, that the z is at right angles to both the x and the y axes, right? You guys explored z-axis before in geometry a little bit? Not at all? Not even a little bit? Just talked about it? No, I don't. But just mention that there is a z-axis, right? But it's at right angle. It's perpendicular to the xy plane, right? Or it's normal to the xy plane. Yeah. Okay. Now the really cool thing that'll trip you out is that if you want to add a fourth component, it is possible. Yes, it is the fourth dimension. And the other axis, whatever you want to call it, the W axis is usually what it's called. It's not necessarily time. Is orthogonal to these three. Yes.
I was told the fourth dimension is everything that can and moves pretty much that.
I don't know where you're going with that.
Well, I mean, like, I was told like that's what the fourth dimension is.
Is everything that is what?
Can and moves, like
Like anything
Oh.
that ever.
No.
That's
Well, let me put it this way. There are many other dimensions. Okay. If we were to look at this into a fourth dimension, okay, a fourth physical dimension, it wouldn't be what's described as that. There are other dimensions out there, and so if you were to look at a fourth dimension, okay, some people, time is a fourth dimension, right? So we have up, down, left, right, forward, back, and time kind of moves us. Right, there's the arrow of time that goes forward. There are other dimensions out there that if we only look at these three plus that one, that is considered a fourth dimension. Right? Okay. We're not dealing fourth dimensional stuff in here at all. Just it's interesting that this can keep going up, and there's always an orthogonal axis, and there can be 5-dimensional axes and 6-dimensional axes. The point is, if they are orthogonal, changes that happen in one axis are independent of changes that happen in any other axis. Acceleration that happens in the x-axis has no effect on what happens in the y-axis. Actually, I need to put in here mutually. They are mutually, mathematically independent. If you have an acceleration, if you have a vector that is acting in the x direction, it doesn't have an effect on what's going on in the y direction. This is important when we start thinking about two-dimensional motion. Motion through the x-axis and y-axis, or if you look at the trajectory of a baseball. Okay, baseball gets hit right here. What causes this parabolic path is if it's sent up with this initial velocity, this initial velocity has a v0 x and a v0 y. It has an x direction and a y direction. A value that goes up and a value that goes to the right. Yeah? That make sense to you guys? Okay. As it's in the air, there's only one force acting on it. Which is what? Baseball's hit up in the air. What's the force acting on it? Gravity. What direction does gravity act? In what direction does gravity act? Down, or in this case, the negative y direction, right? At any particular point, our baseball experiences an acceleration in that direction. Does it experience a direction in the x direction? An acceleration in the x direction? Is there anything after it leaves the bat? Is there anything slowing it down or speeding it up in this direction. Forget about air resistance.
Okay.
No. It travels at a pretty much constant velocity out. Yeah? Okay. So when Aaron Judge hits a 570-foot home run, monster of a baseball player, okay, he's giving it horizontal velocity and he's giving it vertical velocity with the swing of the bat. Gravity determines when it returns to the ground. But the more velocity he gives it this way means the further it goes before it comes back down. Yeah? Time is time. Time is the same in all reference frames that we're worried about. Okay, if you get into start going really, really fast, talk about relativity, time changes, but we're not worried about that here. So the time that it takes for it to go up and come back down is equal to the amount of time that it's traveling in the air. Okay, so the distance that it covers would be equal to its x velocity times the time, right? But how long is it in the air? Well, now we have our y velocity for it to go up and come back down, right? And we'll talk about that, okay, at a later time. But those two velocities are independent of each other. But our total velocity vector equals our x component plus our y component. That's for velocities. If you have a force, okay, if this is our force vector, it has a component. If you have a force that is acting at 53 degrees in that direction, oh, by the way, this amount of force in that direction is also a magnitude and a direction. You guys with that? Okay. This force can be broken up into a y component and an x component. Yeah? We can determine these values. You with me? Okay. We determine these values. This side over here is the sine side for this 53 degrees. Right?
Yeah.
So this side over here, F equals our force times sine 53 degrees. And this side over here is going to be and so we can take our force with a particular direction and divide it up into component parts, into an x direction and a y direction. Okay. That is our addition of, that's where we are right now to our addition of vectors. Okay? Questions?
So what is f of x and f of y? What would that
Sorry?
would that be like acceleration, or would that be
Well, this would lead to this would give you mass times the acceleration in the y direction. This would give you mass times the acceleration in the x direction.
oh. So it's all just kind of just
Okay.
acceleration.
What's that?
Never mind.
Well, remember that they're orthogonal. They're at right angles to each other. So the math in one direction is independent of the math in the other direction. That whatever's going on horizontally doesn't affect what's going on vertically. Okay? Except for time. That's certain things. Ball goes up, comes down in a certain amount of time, right? That amount of time is equal to how far it traveled. It is multiplied by velocity tells you how far it traveled. The time still crosses the orthogonal barrier, but none of the other math does. Okay? This is enough to get you into chapter 5. I do have some problems for you guys to do in chapter 5 tonight on your homework. I need to pull that up real quick. Okay, it's going to be on Classroom, but it is in chapter 5. I want you to do 1, 5, 7, 11 through 13, 17 through 20. So it's 1, 2, 3, 4, 5, 6, 10, but they'll be pretty short in chapter 5. Okay, and they're scattered throughout the chapters, so I can't really tell you what page they're on. It just starts in chapter 5. Okay, chapter 5 starts page 119.